Okay, let's get started. So we're going to use the first half of the lecture to go through the last chapter on the net change theorem. And then in the second half of the lecture, we'll go through some L'Hopital's rule revision. So I have 10 questions here for you to get some points. So we have the second period, so we'll see how many we get through. Okay, so the remaining questions that we don't get through, I will post on Learn, and then you can go through them yourselves. Okay, so before we get into the net change theorem, just quickly recall the fundamental theorem of calculus. Okay, so part 1, as we called it. So this was the integral from a to b, little f of x dx was equal to the antiderivative at b minus the antiderivative at a. Okay, so we've used this quite a bit now. Okay, so inside the integral we have little f, and then on the right-hand side we have the antiderivative, which we call capital F. Okay, now what happens if we replace that integrand, little f, with a derivative? So consider the integral from a to b of f prime x dx. Okay, so f prime, that's just a function, so we're integrating a function. It just happens to be that this function is the derivative of some other function. Okay, so any ideas on what will be on the right-hand side? Okay, so we have FTC part 1. If we're integrating a function, we take the difference of the antiderivatives. If we integrate a derivative, what will be on the other side? Any ideas? Yeah? Got an idea? The original function. Yeah, that's correct. So on this side, we're going to have f at b minus f at a. Why? Because if capital F is the antiderivative of little f, then the original function is the antiderivative of the derivative, right? Because they cancel out. So here, this f is the antiderivative of f prime, just from what we know about antiderivatives. Okay, and just note, I put the antiderivative. We know it should be a antiderivative because there's more than one. We can always add the plus c, but we know that from FTC1, we can always add a constant, but that will get eliminated on the right-hand side. So here we can just use f. We don't need to add a constant. Okay, it doesn't matter what that constant is. Okay, so this is just something to note. Now, why is this useful? So this is useful in a lot of applications where we are considering the change in something. Okay, so there's a few classic examples that we'll go through, but this does extend to anything where you have a change in something and we want to add up these changes to get a net change. So net change theorem. Okay, so the first example is a leaking container. So let's say we have a leaking cup or container. Okay, it doesn't matter what you're considering. So we have some sort of container filled with water, there's a hole in it, and it's leaking. So let's say the rate of change of the volume, or the rate at which it's leaking, is given by some function. So dV by dt is, let's say, 1/2 t squared plus 2t plus 1, something like that. That's the rate of change at which the water is leaving this container. Okay, so we can measure that. We can see how much it is. Now, what we want is to know what is the total amount of water that is lost over a given period of time. We know the rate at which it's leaving. So if we know from T0 to T2, for example, what is the total amount lost? So that's the question we're asking ourselves. So question, what is the total amount of water lost. Okay. So we can think of this dV by dt as an infinitesimal amount of water that is lost at every instant. So the amount of water lost, let's call it dV, is this dV by dt times dt. Okay, so we've seen that before. So we know the rate at which the water is being lost. So over a very short amount of time, this dV is the amount lost. Okay, it's a small bit lost every instant in time. If we want to know the total amount of water lost, we add up all of these infinitesimal amounts. So this dV is the amount lost every instant. So we just add all of these amounts up and we get the total amount. Now this is an infinitesimal, we can't just add them. If we're working with infinitesimals, we don't add them, we integrate them. So the total amount is equal to not the sum of the infinitesimal amounts, but the integral. So we have the integral from t1 to t2 of dV, the little bit that's getting lost, but dV is dV by dt, dt. Okay. And here we see that this has the same form as what we started with. We're integrating a derivative, and on the right-hand side of that, we're going to get the change in the volume, because the integral of dV by dt will be v. So we're going to take v at the end point minus v at the initial point. That gives us the change. Okay. So this is v at the t2 minus v at t1. Okay, that's quite obvious. Okay, so again, integrating up the change from some t1 to t2 is the same thing as taking the final minus the initial. Okay, so you would have seen that in physics in high school. If you want to know the change from some initial to final, you take the final minus the initial. Okay, so we've all seen that before. Okay, so let's have a look at this example again. So we have 1/2 t squared plus 2t plus 1. That is dV by dt. What we want to find is the volume. Okay, so let's say t1 is 0 and t2 is 2. So from time 0 to time 2, what is the total amount lost? Okay, so again, this total amount. Okay, that's going to be the integral from 0 to 2, dV by dt, so that's 1/2 t squared. Okay. Then we've got plus 2t plus 1. dt. So from this, we can find the volume by integrating that, and then taking the difference, the volume at the end point minus the volume at the initial point. That's the change in volume, which is what we want. Okay, so integrating this, that's easy. So that's going to be 1/6t cubed plus t squared plus t. Okay, so everyone should be able to do that quite quickly by now. Okay, so if you're still struggling to find the antiderivative quickly, please go back to the previous tutorial so that you can practice that. Okay, from 0 to 2. Okay, so integrating polynomials, that should be muscle memory by now. Okay, so we can substitute 2, that's our upper bound. Substituting 0, that doesn't do anything, so we can leave that out. So we're going to have 1/6 2 cubed, that's just going to be 8. 2 squared, that will be 4 plus 2. Okay, so 8/6 plus 6. And then you've got your calculators, you can work that out quickly. So this is the net amount of water that has left the container. Okay, so again, what are we doing? We know the rate of change of something, and we want to find the net change. So in this example, we want to find the net change in volume. So we're looking for the final volume minus the initial volume. How do we get the final volume minus the initial volume? Yep, from here. V at T2, that's the final volume, minus V at T1, that's the initial volume. How do we get that? We integrate the rate of change. Okay. So very similar to what you've seen in high school with taking final minus initial, but here to get the final and the initial, to get that function V, we have to integrate. Okay. So in high school you didn't need to do the integration, but that's what was happening behind the scenes. Okay, any questions on this? No questions. Okay, let's have a look at example 2. Distance and velocity, displacement. Okay, so for those of you who did physics in high school, this will be very familiar to you. Distance and displacement, they're fairly similar, but there is a difference between them. It's quite similar to how there's a difference between speed and velocity. Okay, so if you're thinking distance and displacement, you're also thinking about speed and velocity. Okay, so what is distance and displacement? Okay, so this is for those of you who have forgotten or you didn't do physics. So imagine we've got some coordinate system here with a particle at the initial point I, and it's moving to some final point F. Now, to get from I to F, it's going to take some path. So maybe something like this. Okay, the length of this path, that is the distance. Okay, so the actual path traveled, that is the distance traveled. Okay, what about the displacement? The displacement is just looking at the strict difference between the final and the initial. So that is this. Okay, so you can think about it in terms of your vectors that you've done before. You have the final position, the initial. You can think of it as a vector going to the final, a vector going to the initial. Take the difference, that gives you that straight line vector from I to F. That's the displacement. Okay, so if you have, starting from I, you're going to F, the displacement is that straight line distance there. Okay, you can think of it in terms of the vector, going from the initial to final. The distance is the actual path taken. So that's that longer wavy line over there. Okay. So that's in 2D. You can do the same thing in 1 dimension. Okay, so let's say this is X, and we start out over there. Okay, so you can think of that as the origin. So what we can do is take this particle and make it move around. So let's say it goes to this point. So it starts here, it goes to there, then it moves back and goes to here. Okay, so it starts from 0, goes to 1, and then goes back to 2. We can think of this as minus 2, okay, because it's on the other side. So what is the distance traveled by this particle? So it started from 0, and it went to point 1. So that's going 1. Then it's going backwards to minus 2. So it's going 1, then it's going back to the origin, so that's plus 1. And then from the origin to minus 2, that's another 2. So it's going 1, 1, and then 2. So what's the total distance? 4. Okay, so that's the distance is 4. We actually follow the particle and we see it traveled a distance of 4. What's the displacement? The displacement doesn't care about how you get to the end point. It's just the end point and the initial point. So it started from 0. It ended at minus 2. So what's the displacement? Okay, someone said 2. It's not 2, it's minus 2, because we're going in the negative x direction. So for this example, we see that the distance was 4, but the displacement was minus 2. So the displacement has that sign attached to it. Displacement will be positive if you're going in the positive direction, or you end up somewhere positive. And displacement is negative if you go in the negative direction. So here we ended up at minus 2. So we traveled left. So we say the displacement is minus 2, going left. If we ended up at positive 2, then the displacement would then be positive 2. Okay, so please note that distance is always positive. You will never ever get a negative distance. Distance is the actual distance that the particle traveled along, whatever the path may be. Displacement can be positive if you end up on the positive side. It can be negative if you end up on the negative side. It depends on where you started and where you ended. Okay. Any questions about that difference between the two? Okay, so everyone's okay with that. Okay, so now that we know the difference between distance and displacement, let's look at the difference between velocity and speed. Very similar idea. Speed is your distance over time. That's going to be positive. Okay. If you travel a certain distance, that's positive, because distance is positive. Over an amount of time, that's positive. That's how you get your speed, distance over time. What about your velocity? Velocity is not distance over time, it's displacement over time. So your velocity will be negative if you're going in the negative direction. Your velocity will be positive if you're going in the positive direction. Okay. It goes with the displacement, whether it's positive or negative. Okay, so let's write here. Speed, that's going to be distance over time. And going with displacement, we have velocity, which is displacement over time. Okay, so we understand speed, we understand velocity. Now, what we want to do is very similar to what we did with that rates of change of water volume. Let's say we know the rate of change of distance. What is the rate of change of distance? That's the speed. If we know the rate of change of distance, we can add up all those changes and we get the net result, which will be the distance. If we know the rate of change of displacement, which is velocity, if we know that, we can add up all of those changes and we can get the net displacement. Okay. And just a note, we can write speed as the absolute value of velocity. Okay, so remember, velocity can be positive or negative depending on where we're going. If we take the absolute value, that just gives us like the length of the velocity vector or the magnitude of the velocity, however you want to think about it. We call that the speed. Okay, any questions on that before we move on? Okay, so everyone's fine with that. Okay, so let's look at an example. So let's say we know the velocity is 1 plus t squared minus t. Okay, something simple like that. We want to find the distance covered in some time interval by adding up all the infinitesimal distances. And we want to find the net displacement, again, by adding up the infinitesimal displacements. Okay, so let's say we're going from t equals 0 to t equals 1. Okay, just to make things simple. So the first thing that we want to do is find the displacement. So the displacement is equal to the integral from 0 to 1 of the infinitesimal displacement, the tiny little displacement. So if we know it has velocity v, if we multiply that velocity by a very small amount of time, we're going to get a very small amount of displacement. So v dt is a small amount of displacement. We want to add up all of the displacements, so we integrate v of t dt. Okay, so that combined bit on the right, v dt, that's a tiny bit of displacement. We want to add all of them up, so we integrate, and then that gives us the net displacement. Again, adding up all the little changes gives us the net change. Okay, so this is going to be the integral from 0 to 1 plus t squared minus t dt. Okay, this is quite simple to do. Again, just take the antiderivative. So that's t plus 1/3 t cubed minus 1/2 t squared from 0 to 1. Again, if we substitute 0, we're just going to get 0, so we don't have to worry about that. We can just substitute 1. So we get 1 plus 1/3 minus 1/2. Okay, so we get 1/2 plus 1/3. Okay, a little bit of cross multiplying. We get 3 plus 2 over 6. 5 over 6. Okay, so that is the displacement. So this particle started wherever, and then over this time interval, it ended up at positive 5 over 6, okay, on the x-axis. So we can even put a plus there, so we know that it ended up on the positive side of the x-axis, right? Because this is displacement. It can be positive, it can be negative, it depends on where you end up. Okay, so that's displacement. What about the distance? So the distance is equal to the integral from 0 to 1, okay, as we had before. But now we're not integrating the velocity because velocity was linked with displacement. We're integrating the speed because the speed is linked with distance. Because remember, speed is distance over time. They link together. So here we want to integrate the speed dt. Because if we take the speed and multiply it by dt, that gives us a small amount of distance. Adding up all of these small amounts of distances gives us the net distance, which is what we want. Okay, but we're not given the speed, we're given the velocity. How do we get from velocity to speed? We take the absolute value. You can think of it again as the magnitude of the velocity, which is the speed. So we're looking at the absolute value of what we have there, the 1 plus t squared minus t. So absolute value of 1 minus t squared plus t. Okay. So is it 1 plus t squared? Yeah, 1 plus t squared minus t. 1 plus t squared minus t. Cool, thanks. Okay, so we're integrating the absolute value. Now, we've seen this before when we were doing the area between curves. We took the absolute value of the upper one minus the lower one, and then we had to split that function over the different domains depending on if the function was positive or negative. Okay, so here we're going to do the same thing. We've got the absolute value of this thing, okay, and we want to know where is it going to be positive, where is it going to be negative, so that we can put the appropriate minus sign. Okay, so here, just on the side, we have absolute value 1 plus t squared minus t is equal to something. It's going to split up. It's going to split up into a part where the inside part is negative, and then we need to remember to put the minus sign. It's also going to split up into the part where it's positive, but since it's positive, we can just leave it like that. Okay, so we're going to have a negative part. And then for the negative part, we put a minus sign in front to make it positive again. And then we're going to have a positive part. Now, it's already positive, so we can just leave it alone. Okay, how do we find this negative part and positive part? Okay, we need to look for the roots of this thing. And then once we have the roots, we can see where it will be positive and negative. Okay, sometimes it may not have roots, but we'll look at that separately. Okay, so here, just a little sketch. It might look something like this. Right, it's a happy face parabola because it's plus t squared. We don't know exactly where the roots are, but it might look something like this. So we have root 1 over here, root 2 over there. We see that here's positive, here's negative, here's positive. So we see that in that middle region between the two roots, that's where it's negative. That's going to be in the top part. Before the first root and after the second root, it's going to be positive again, so that's going to be in that bottom part over there. Okay, so let's see where those roots are. That will tell us where it's positive and where it's negative. Okay, so we've got this 1 plus t squared minus t equals 0. Let's rewrite it in the form that we know. So that's going to be t squared minus t plus 1 is equal to 0. Okay, now we know our coefficients a, b, and c. We can use the quadratic formula. So t is equal to minus b plus minus the square root of b squared minus 4ac all over 2a. Okay. Now, you can put this in your calculator, but there's going to be a problem. Look inside the roots over there. We're going to have 1 minus 4. But that's going to be a minus 3. So we're taking the root of minus 3. We can't do that. That's not going to be a valid number. If you were to put this in your calculator, you're going to get an error, and it's going to be a problem. So you need to see when can you actually find the root, and when can't you find the root. So don't just put it straight in your calculator and then write down error. That's not going to work. We need to think for a bit. So we see that there's no roots to this. Okay? So there's no roots, and it's a happy face parabola because it's plus t squared. So what picture do we actually get? There's no roots, but it's still happy face. What picture do we get? Any ideas? Yeah? It's always above the x-axis. Very good. So our picture can be updated to now look like that. Okay, we see we tried to find the roots. We couldn't find anything. We know it's a happy face parabola just by looking at t squared, so it must look something like that. Which means it's always positive. There's no negative part to it. So the absolute value of this function is just the function. It's always positive. So when we're integrating, we can drop the absolute value. Okay, so the distance is equal to the integral from 0 to 1. So here we had the absolute value. We proved now it's always positive. We can drop the absolute value. So we get 1 plus t squared minus t. Okay, we did this before. So we can just write the answer down. So that is 5 over 6. Okay, so what does this mean? It means that this particle started at the origin. It moved along the x-axis, but it never went back. It just went straight along the x-axis, which means the displacement is equal to the distance. Now that's not always going to happen. Okay, if the particle goes forward for a bit, and backwards for a bit, and then forwards again, the displacement and the distance will not be equal. In this case it is, but it won't be in general. Okay. If we had a different velocity where the velocity did go to negative for some region, then the distance and the displacement would not be the same. Okay, and you can see that in the tutorial work. Okay, there's some examples of that. All right, any questions on this? No questions. Okay, so please just keep in mind, in this example, the distance and the displacement were equal, but that does not happen in general. Okay, please look at the tutorial exercises for more examples on that. Okay, so last example. Densities. Okay, so this is used quite a bit in engineering, so you'll see it later on. Okay, so what is a density? Now, you should be fairly familiar with what a density is from your high school work, but we'll go over it again. So here we're looking at volume densities. So let's say we've got some amount of mass, and it takes up a certain volume. We want to know exactly how much mass is in each little bit of volume. Okay, so here, let's say we've got a box. Okay, and let's say it is completely filled with water. Okay, all the way up. What is the mass per volume throughout the box? So usually we write it as rho for density. It is the mass per volume, mass over volume. Here, if we fill this all the way up with water, we know the mass, right? We know the mass of water. We can work out the mass of this. We know the volume. And if all of it is water, then at every point in the box is going to have the same density. So at this point, we're going to have some density, and at this point, it has some density, because the whole volume is filled with water. It's the same stuff all the way through. So across the volume, it has the same density. Okay, does that make sense? Okay, who does not understand that? Okay, let's look at another example. Okay, so we have our box again. Okay, but now it is partially filled with water. This bottom region is water. The top region is going to be air. Now let's look at the density across the box. In that bottom region, the density is going to be very high because the mass of water is much greater than air. So this bottom part has a high density. The top part has a low density because it's air, it has less mass. So we can see across the volume here, there's a change in density. Right? The bottom part has high, top part has low. The density is not uniform. Okay, it's different if we look at different parts of this. Now, how do we find the total mass in this box? So the total mass, M, is going to be the density of water for the bottom part multiplied by the volume that it takes up. So how do we get that? Well, density is mass over volume. So mass is density times volume. So it will be the mass of the water times the density of the water. Sorry, times the volume of the water. So mass of the water will be the density of the water times the volume of the water. And then we have the mass of the air. That will be the density of the air times the volume of the air. We add up the individual masses, or we can think of it as the density of the water times the volume of the water, plus the density of the air times the volume of the air. That's the same thing as adding up the masses. Now this is if we have a discrete section of water and then a discrete section of air. We can clearly see the difference between the two. Okay, and they have different densities. What happens if it's not so discrete like this? What happens if the density changes continuously across? So let's say we've got something like this now. We've got a box, but now we're not going to have individual layers. We're going to have a density function across this. So let's say this is Z, and across this we're going to have rho of Z. So now at every point there's a different density depending on where you are. Okay. So if I ask you, what's the mass of the box? We're going to do the same thing as before. We want to add up all the masses of every infinitesimal layer. The mass is the density times the volume. So we're going to do the same thing here. And we want to sum them up. But we no longer have discrete chunks to sum up. We now have infinitesimal layers to integrate. So if we imagine a layer like this, okay, so very thin layer with volume dV. How do we get the mass? It's going to be the density times that little bit of volume, and then we add all of them up. So it will be the integral from 0 to some final z, rho of z dV. Okay, very similar to what we had before. Instead of the sum of the masses, we now have an integral of infinitesimal masses given by rho dV. Okay. Any questions so far? Yes. Rho, that's the density. So going from the bottom to the top, it's made of some different material. So it's like inhomogeneous material. So at the bottom, let's say it has a very high mass, so it will have a high density. And then as you move up to the top, the material changes to have a lower mass. Okay, and then at the top, maybe it will have a lower density. Okay, so just think of it as some type of material, but at the bottom, there might be high density, and at the top, it has low density.
So the function, like, be related to the material, so every time the value changes, it also changes the mass.
That's right, yes. Yeah. So we might have a function like this. So here's Z for the height going up here, and then we have rho. Maybe it looks something like that. So at the bottom, it has like a low density. Then as you move across, maybe you go into a different material with a higher mass, so then the density goes up. And then maybe after that point, you move into another material where the density goes back down, just as an example. Okay, so the density changes across, which means the mass also changes across. Okay, so just an example. Let's say rho of x is equal to 1 plus t squared. Very simple. Okay, so we can imagine this for a one-dimensional object. So it's not a box where we're integrating dv. We've got like a metal rod or something. So here it only goes along x. So the density in this case will not be the mass over the volume, it will be mass over the length. Okay, because we're looking at the length of it. So this will be the mass over the length. Okay, because it's one-dimensional. Okay, so what will the mass be in this case? Let's say at this point is 0 meters, at this point is 1 meter. The density changes like that across. We want to know the total mass. So the mass will then be the integral from 0 to 1, rho of x dx. So all of this together, that will be our infinitesimal mass, a little bit of mass at that point. We add up all the infinitesimal masses, that gives us the total mass. So this will be the integral from 0 to 1. Sorry, not t, that should be an x. X. So 1 plus x squared dx. So this will be x plus 1/3 x cubed from 0 to 1. So this will be 1 plus 1/3, 4 over 3. Okay, maybe kilograms or grams, something like that, depending on how we're measuring the mass. Okay, so if we're given the density across some object, when we integrate the density, that will give us the mass. Okay, so I'm not too worried about the units. Okay, so the question might have units in them. Again, this is a math module. I'm not too worried. But remember, for physics and engineering and so on, the units are important in that case. Okay, but for this module, we're just interested in the number. Okay, any questions? Okay, so these are the three main examples that you should be thinking of with the net change theorem. There are many more cases where this applies. So engineering, math, physics, so on. There's a lot of examples with the net change theorem. But from these three examples, you should have an idea of what we're trying to do. We have some infinitesimal change in something. So that could be the change in distance, the change in volume, the change in mass. Something is changing. We add up all of those changes, or we integrate the changes, and that gives us the net change. Okay. Is anyone not comfortable with this idea? Okay, everyone's quiet. So we'll leave it at that and then go on to the revision.